Okay, so today I'm going to talk about recurrence relations. So what are recurrence relations? So suppose you are given a sequence, you have to find the value of the end term. Recurrence relations help you to find the term using the previous n minus 1 terms. I will give an example. Suppose you have a 2 into n grid. Now you have to tile the grid using either 2 by 2 or 1 by 2 dominoes. And also you can't rotate them. So they must be placed like this only. So suppose n equal to 3. In that case, there are these many ways. I will show all the cases. We can tile the first column using a 1 by 2 domino. In the second and third column with a 2 by 2 domino. One case is when we use only 1 by 2 dominoes. And the other case is the first case but flipped. We place the 1 by 2 by 2 first and the 1 by 2 second. So now how to find for a general term? Let En be the solution for n terms. Now notice that for the last column, last few columns, if you see, you have two choices. Either you use a 1 by 2 domino or a 2 by 2 one. Now, if you choose a 1 by 2 one, then you are left with a 2 into n minus 1 grid. In this case, when you choose a 1, the number of ways to tile this is a n minus 1. So we will write the term here. Now the second case is when we choose a 2 by 2 one. Now in this case, you have a 2 into n by 2 block, and the number of ways to tile it is a n minus 2. This is also similar to the Fibonacci relation. In this way, we are able to express all the terms using the previous terms as well. For example, a1 equal to 1, we will write the base cases separately. a2 equal to 2. Now a3 equal to a1 plus a2 equal to 3. a4 equal to a2 plus a3 equal to 5. And so on, we can write the solutions. Now I will take another problem. In this one, you are given a n minus n grid. N by m grid. Now in this grid, there are two types of cells. One are good cells and the second type is of bad cells. So for example, I'm shading this cell. You can't visit this cell. So these four are bad cells. And now you have to find a number of ways to go from the bottom left cell, this one, to the top right cell. It is guaranteed that these two cells are good cells. Now you have to find the number of paths, and notice that in a path you can only go up or right. So you can't go up, then down and left, and you can only visit good cells. So we have to find the number of paths from bottom left to top right. So now the way to do this is using recurrences. Now, obviously, the number of ways from bottom left to bottom left is one only. We have to find the number of ways to the other cells. So on each cell, I will write the number of ways in which you can reach it using from the bottom left cell. So this is one. This is one. Obviously, all the cells which are reachable from the bottom left one in the first row or first column will be 1. Now this one is blocked, so it will be 0. Now notice that the number of ways to reach the 2, 2 square, this one, the number of ways is 1 plus 1. We can either come from the cell which is just below or just to the left. So 1 plus 1 equal to 2. Now here, in this cell, we can either come from the left cell or the cell just below. The number of ways are 2 plus 1 equal to 3. Now this cell is blocked, so it's obviously 0. This cell will be 0 plus 1. This cell will be 1 plus 0. And so on we will do for all. This one is 0. This one is 0. Now for this cell, it will be 0 plus 3. 3 plus 0, 3 plus 1, 4 plus 1. And so on we can do. So now the number of ways to visit this cell is 90. We can write it a bit formally. Let Aij be the number of ways to reach the cell in the ith row from the bottom and jth column from the left, from the bottom left corner. Now, 0 if bad cell, otherwise. We will take sum the values of the cell to the left and the cell which is just below. And now obviously we need to consider the case when it's the first row, first column. So Aij equal to 0 if I is less than 1 or j is less than 1. So I was going over the basics. So does anyone have any questions about this?
This is essentially the same as dynamic programming, right? This question.
Yes. This is a very classical question. So, okay, now I will be discussing how to get a closed form of a recurrence relation. So suppose a recurrence relation is of the form of the following form. You write An as the sum of Zi into An minus I. The summation of this, where Zi are some maybe integers. So for example, if there are k terms on the right hand side, Zi can be 0 also. So now I've written an in the term. I've framed an according to its previous terms and some coefficients. Now I will define a characteristic equation for this. A characteristic equation for a recurrence of this form will be x to the power k for an minus z1 into x to the power kn minus 1 minus z2 x to the power kn minus 2 and so on minus zk. So for the last term, we do the coefficient, the power of x is 0. For the first term, the power is k. And now this is equal to 0. We find the roots of this equation. Let the roots be R1, R2, R3 and so on till Rk, since it's a degree k equation. Now I will show for the case when all the roots are distinct. So suppose Ri is not equal to Rj for all I less than j. Now in this case, the recurrence relation has the closed form of the form n equal to c1 into r1 to the power n plus c2 into r2 to the power n and so on up till ck into rk to the power n. Now the ci's are the coefficients, and to find them, we see the first k values of the recurrence relation. So I will explain this later with Fibonacci. So we can see the first k equations, and using linear equations, k linear equation in k linear variables, we can find all the coefficients and we can proceed further. If Ri equal to Rj for some I comma j, so suppose a root R appears L times. In that case, instead of this, it will be of the following form. So for example, I will only be telling about one term R, and so on we sum across all terms. So it will be of the form for each repeated root, we increase the power of n. So for example, this is n to the power 0, the first one. This is n to the power 1. And so on we proceed. This will be n to the power k minus 1 into rk to the power n. So are there any questions about this? I will explain with examples also. Okay, so I will proceed. Yeah, I will explain with an example. So for example, we will just take the Fibonacci series. Now in this case, the characteristic equation will be x square equal to x plus 1, which is x square minus x minus 1 equal to 0. So we can solve the quadratic and we will get x is either 1 plus minus root 5 by 2. So it has two roots. Now we will write all the roots are distinct, so we don't need to do multiply coefficients with n. C1 into 1 plus root 5 by 2 to the power n plus C2 into 1 plus root 5 by 2 to the power n. Now I'm listing the initial terms of the Fibonacci sequence. So A0 will be 0, A1 equal to 1, A2 equal to 1, A3 is 1 plus 1, 2, and A4 is 1 plus 2, 3, A5 is 2 plus 3, 5, and so on. Now, since there are two roots, we only see the first two equations, A0 and A1. A0 equal to C1 plus C2. Since n will be 0, this term will become 1 only. Wait 1 second. This will be a minus. And A1 equal to 2A1, in fact, 2A1 equal to 1 plus root 5 C1 plus 1 minus root 5 C2. So now we know the values of A0 and A1. If we write them, we get 0 equal to C1 plus C2. And the other equation is 2A1. So this will be 2. Now we will expand the part below. We get C1 plus C2 plus root 5 C1 minus C2. Now C1 plus C2 is just 0. So we can, this will be 0 and I am erasing this. Yeah, you can ask if you have any question. Okay, I will proceed. So now we have the values C1 plus C2 and C1 minus C2. So now we can easily calculate the values. So C1 will come out to be 1 by root 5. We will just add and subtract the two equations. And C2 will just come out to be its negative. So is this part clear to everyone? How I found C1 and C2 from the Fibonacci series? Okay, so I'll proceed. Now we have just found the question. So n can be written as 1 by root 5 plus 1 by 2 to the power n minus 1 by root 5. Root 5 minus 1 by 2 to the power n. This is the n term of the Fibonacci. You can check for higher values and it will satisfy. So this is an example. So there's a question. Okay, so there is a proof, but I won't be going over it here. Why this method works? Basically, it's not that hard to show that it works, that the K equations generate K solution. We can just show that the coefficient ratio of the coefficients is not same for all the terms to show that they generate solutions. Okay, so there are more questions. So I will send the link to the proof after the class. So I will now show another classical example. If since there might be people who are very new to recurrence relations, suppose you are given a set of stairs. There are n steps, and now you have to find the number of ways to reach the top, and you can only take 1, 2, or 3 steps at a time. In this case, the recurrence relation will be n minus 1. If you take the first step, you have n minus 1 more steps to go, and you can just tweak an minus 1 plus an minus 2 plus an minus 3. Now I also want to tell one more thing about the grid equation. Now suppose there are no bad cells. In that case, we don't even need a recurrence, and we can find a straightforward solution, which I will explain. So now it's a n into m grid. We have to go right exactly n minus 1 times. And we have to go up m minus 1 times, or vice versa. It doesn't matter. So now in total, we take n plus m minus 2 steps. And we can take these steps in any order. So out of these steps, any n minus 1 can be right, and any m minus 1 can be up. So the number of ways comes out to be n plus m minus 2, c n minus 1. So can everyone understand this formula? If they are all cells are good, you can visit all cells.
Yeah.
Okay, so I will now discuss some problems. Show that there exists a non-zero Fibonacci number that is divisible by n. N can be any given natural number. So it holds for all n that you can find the Fibonacci number divisible by it. So now the proof is, I will first write the recurrence. Now you have to find a non-zero one. So you can't write is 0 equal to 0. So now if you first look at the first 3n square terms, if you look at the pairs ai comma ai plus 1, notice that modulo n, we will define the sequence modulo n, and we have to show that ai equal to 0 exists, I is greater than 0. Now, if we look at the consecutive terms pairs, realize that they can take only n square values. Since both have n choices. Now, by PHP, there must be at least 2 pairs which give the same results. Since there are 3n square minus 1 pairs and only n square possible pairs of values, at least 2 must be the same. So let ai equal to aj and ai plus 1 equal to aj plus 1. So is the PHP part clear to everyone? Okay, so I'll proceed. Now notice that if we are given 2 terms, say c comma d, this is the kth term. Let's take a different variable. Then we can determine all the terms of the Fibonacci series. This will be c plus d, c plus 2d, 2c plus 3d, and so on. And now this term will be d minus c, since the sum of the first two must be equal to the third. Okay, so I have a question. So can you please tell what do I have to explain? So can you tell what should I explain? Okay, I will go over it again. I have not explained the entire solution. I am just explained some part of it. So now we define the Fibonacci relation this way, and we define it modulo n. We have to show that ai equal to 0 for some value. Now we look at the first 3n squared terms, and if we look at the adjacent pairs ai comma ai plus 1, there are 3n square minus 1 such pairs. Then notice that they can only take n square distinct values, the values, since the first can take n and this can take n, so only n square values. Now if there are 3n square minus 1 terms, which is strictly greater than n square, at least two will have the same values by pigeonhole principle. So can you understand now? Okay. So n square values are basically x comma y can be the possible values, and x is between 0 and n. Y is also between 0 and n. So it's only n square possible pairs. So now I hope it's understood. Okay, we'll proceed. Now, I was saying that if there are two terms, we can determine the entire terms. Of course, the sequence is defined modulo n only. So like this will be 2c minus d and so on. Everything is defined modulo n. And now we can find the entire sequence. Now suppose that we have a pair I where ai equal to aj and ai plus 1 equal to aj plus 1. Now in this sequence, if you notice that ai minus 1 equal to ai plus 1 minus ai equal to aj plus 1 minus aj, since the pairs are equal to aj minus 1. And so on. Using induction, we can show that ai plus k equal to aj plus k for all k, such that the sequence is defined. Obviously, the terms must be non-negative. So is this part understood? Okay, so I'll proceed. Now we have taken I is less than j. Obviously, a0 is equal to 0. So if we substitute k equal to minus I, we get ai minus I equal to aj minus I. A0 equal to 0 equal to aj minus I. Now, aj minus I we have shown to be 0 and j minus I is greater than 0. Now this is 0 modulo n. So we have shown that there is a number divisible by n. Is this part clear to everyone? Using this, we can also show that a number is not only divisible by n, we can also show that there's a number which leaves one remainder mod n for n greater than 1. And so on for 2, 3, 5, 8, 11, and all those terms. Okay, so this problem is done. We have shown that there exists for all n. Now the next problem is, consider a 1 into n natural rectangular board made up of n unit squares. There are three types of tile: 1 by 1 red tile, 1 by 1 green tile, and 1 by 2 blue domino. Let Tn be the number of ways of covering the rectangular board by these three types of tile. Prove that Tn divides T to n plus 1. So I'll give you a few minutes to try this question. You have to show that this term divides the other. There are three tiles. And there's an endless supply of all tiles. So I'll shade by the colors. There are three types of tiles and you have a 1 into n board. Show that the number of ways of coloring n size board divides the number of ways of coloring a board of size 2n plus 1. I will give you a few minutes to try this question. So after a few minutes, if anyone gets a solution, then they can tell it. So for a hint, I will just put the recurrence, which should be easy to get. There are three options. Two of them lead to a board with n minus 1 remaining tiles, and one leads to a board with n minus 2 remaining tiles. So if you get a solution, you can write in the chat that I am able to solve.
Do we like solve the recurrence and then show the divisibility manually, or
Well, that method is possible, but there's a simpler solution as well without getting the closed form recurrence.
I think
So
also
I'll,
close from there will be like irrational number, right? So that might be hard, I guess. Anyways.
yeah, that is a more bashy way to find the solution, but it also works.
Okay.
But you can try coming up with a clever solution. Okay, so Zaman has typed in the chat, and he has a good point. Well, not exactly, but yeah, the solution has the right idea. So basically, yeah, he is saying that for En, if we find if the kth and k plus 1 tile are covered by square are covered by different tiles, we can just do ak into an minus k. But if they are covered by the same tile, obviously it must be the 1 by 2 tile. And so we can do ak minus 1 into an minus 1 k minus 1 base. So that is correct. And it should be actually be 2k ak into an minus k in the first term. So now if we do proper substitutions for n and k, we can get the desired result. So I'll explain the solution now. So can I explain, or you want a few more minutes to try? Okay, so now I'll explain the solution. So suppose there are 2 into n minus 1 squares. Let this be the center square. We will number it 0. We will number the left squares in negative and the right squares in positive. So now we will find the recurrence based on what type of tile is covering the cell 0 and what's its location. So I'll go over the cases one by one. So suppose the tile is being covered by a blue. Wait, I will see the colors once. So one by one red tile is covering it. Now in this case, the left and right side are divided into two parts, and we can just write it as En into An equal to An square. Now, if it's being covered by a green tile, we can also write it in the same way as An squared. Now there are two more cases based on if it's being covered by the other tile, which is blue in color. So now in this case, suppose that it's the right end of the tile, the center square. In this one, the left space has n minus 1 and the right has n. So it takes en minus 1 into en ways. And the last case is similar, in which it's the left end of the tile domino. In this case, there are n terms to the left and n minus 1 to the right. So we can write it as en into en minus 1. Now, if you add all these terms up, I will get a new slide. Then you will get 2an squared plus 2an into en minus 1, which is obviously divisible by en. And so an divides a to n plus 1. So did everyone understand the solution? In fact, this problem is from INMO only. 2018. So now somebody had written a statement for a general K. I will explain that also. It's quite similar. So suppose we have a 1 into n board. Now for some K greater than 1 and less than n, we can find the value an using smaller terms of using how the kth square is colored. So now in this case, the first term will be, suppose it's covered by 1 tile. There are two colors, two ways to choose. And the left hand side is k minus 1 size, right side is n minus k. So it's 2ak minus 1 into an minus k. Now if it's covered by a tile of size 2, then there are two possibilities. One is this one and the other is this one. In the first one, it's ak minus 2, since k minus 2 tiles are at the left, into an minus k. And in the second one, k minus 1 tiles are at the left, and the right side has an minus k minus 1 tiles. So is this clear to everyone? Basically, what I explained is almost same as this, but we substitute n comma k as 2n plus 1 and n plus 1, which I believe should give the same formula. Yes, it indeed does give the same formula if you see. So did everyone understand this? How we wrote it? So I will proceed to the next question now. So now in this question, you can read it. Let Tn denote the number of arrangements of the integers 1 to n into a sequence 1 to n. Basically, you need to find a permutation, the number of permutations satisfying a specific condition that. Okay, so can you tell what should I repeat? Someone has a doubt, so can he tell? So can you tell like what doubt do you have in the previous solution? Hello. Okay, so I will proceed. We have to find a recurrence satisfying the we have to find the number of permutations satisfying a condition that ai is greater than a to i for all I comma 2i between 1 and n, and ai is greater than a to i plus 1. So now the one part of the question is find the recurrence for t 2n minus 2 and 2 to the power n minus 1. So now this is the question. I will give an example. So suppose you have a sequence 1, 2, 3, 4. I change it a bit. Suppose you have a permutation 1, 2, 4, 3. Now 1 is greater than 4, 1 is greater than 3, and 2 is greater than 3. Basically, we have to check for pairs of the form I comma 2i and I comma 2i plus 1. So 1, 2, 1, 3, and 2, 4. These are the values, the conditions I've written. So now this is a satisfying permutation. There, even in the question, they have given that T3 equal to 2. There are only two possibilities. Wait, in this question, I have done the opposite, that it's smaller. Yeah, in the example, I by mistake explained when the AI is less than A2I, but the number is obviously same since we can substitute I with n plus 1 minus I. So is the question clear to everyone? This is a less than. So is the question clear to everyone? Basically, a permutation is a ordered arrangement. Suppose there's an array of size n. So you have to arrange the number n numbers in some order. And now you have to find a recurrence for t 2 to the power n minus 1. So I'll give you a few minutes to try, maybe 2-3 minutes. You just have to find a recurrence. You don't have to find the closed form, but that is easy actually. Not for Tn, but t 2 to the power n minus 1. So I'm giving you all a few minutes, and if you find the solution, you can write in the chat. So does anyone have any ideas? So the Zaman's idea is right that even is fixed, which is the minimum element. He's right. Oh wait, I have to send the message to everyone. So you can try for a few more minutes and I'm sure you will be able to solve this using recurrences. Okay, so I will give you an idea that you can define an equal to t to 2n minus 1. And also it's a binary tree, I have to tell you that. Now, if you like construct a tree of the pairs I comma 2i, I comma 2i plus 1, where they are connected by an edge, then you will get a tree of this form. This is an important observation. And now since it's a perfect power of 2 minus 1, it will be a complete tree. So the last layer will be completely covered. Basically, there will be one node in the first tree, two in the second depth, second level, and 4 in the third level, and so on, up to 2 to the power k equal to k plus 1 minus 1. Okay, so someone is asking what is a tree? So basically, a tree is a graph of n nodes. There are n minus 1 edges, and you can reach any node from any other node. Basically, like n is equal to 4 in this case. I'm constructing a tree. 4 nodes, 4 minus 1 edges, and each node is reachable from all other nodes. For example, we can reach all the nodes. This is another graph. It also has 4 nodes and 3 edges, but it's not a tree since it's not connected. Also, there's exactly one path from each node to any other node. So I hope I'm clear here. Oh, wait, I was on mute. So we connect. Was I on mute the whole time or just right now?
Just for now.
Okay. Okay, then did you understand the tree now? Okay, so I will tell the recurrence. Was anyone able to find it who hasn't done the problem before? I believe that some of you would have done it. Yes, I mentioned binary tree. So binary tree, each node has 2 children or 0 children or 1 child. So maximum degree of a vertex is also 3. And the root has vertex of at most 2. And so now, if you notice, after defining an, we will construct a tree, node 1, node 2, node 3, node 4, 5, 6, 7, and so on. The nodes will the each level will have the nodes from 2k to the power 2k plus 1 minus 1. So did you all understand this, how it's a binary tree? Since it's a perfect power of 2 minus 1. Okay, so now if you notice, I will add a few more edges. If you notice that if there's an edge from node I to and node J are connected by an edge, and I is less than J, then AI is less than AJ. This follows from the condition of the problem. Yes, it's the same problem. And now, if you notice that from node 1 to 2, there's an edge. So A1 is less than A2. And so on. By induction, we can show that A1 is less than AI for all I greater than 2. So now, since it's the minimum element, A1 equal to 1. And now we have 2 subtrees left. If you see, the subtree of nodes 2 and 3 will have all the other vertices, right? And each of them will have size equal to this S2, which is size of subtree will be this. S3 is also equal to this. Since it's a perfect tree, it's completely symmetric also. So did you all understand this? We already know the previous values, like if you have to find an, and we know a1, a2, and to the 2an minus 1. So did you all understand this part where we take the 2 subtrees? Basically, a subtree is a node and all its descendants. So did everyone understand the subtrees, the 2 subtrees? Okay, I'll proceed. Now, notice that we have 2 to the power n minus 2 numbers remaining. The others have the one number has been used. And now we half of them have to go to the left half and half of them have to go to the right half. So there are 2 to the power n minus 2, C 2 to the power n minus 1. Wait, they did get cut, so I will erase it. So out of these many numbers, half of them exactly will go to the left half and half of them will go to the right half. There are these many ways of choosing half of the numbers. And now notice that if I asked you to solve the problem, not for permutation, but for a set of n distinct numbers, then also it's the same thing only. The numbers get mapped to 1 to n by sorting them. So now the number of ways of solving the left half is an minus 1, which is also equal to t n minus 1. And the number of ways of solving the right half is also similar, an minus 1, which is also equal to t 2 to the power n minus 1 minus 1. So n equal to into an minus 1 square. So did everyone understand the recurrence? How I came, how this recurrence works? If you have any question, you can ask. This was the main part of the problem. Okay, so I will repeat. Now, like you all can speak also by unmuting. So can you tell what is your doubt? Can you tell which part I should repeat? Like you understood the subtree part, right? Okay, so did you understand how half of the numbers are sent to the left half and half are sent to the right half? These are exactly, so did you understand the combination part 2 to the power and this term? Did you understand this term? Okay, so this is basically NCR is the number of ways of choosing R objects out of N objects. So here there are 2 to the power N minus 2 numbers and we have to choose half of them, these many numbers, which will go to the left half. And so this is based nothing but same as choosing K balls out of N balls. So did you understand this part now? Okay, so now the number of ways of solving the left half is an minus 1 and the number of ways of solving right half is an minus 1 also. Now notice that the numbers may not be a permutation of 1 to 2 n minus 1 minus 1. These may not be a permutation, but they will still work because they are all distinct and so you can map them. I will show how you can map them. So for example, if you have 4 numbers 1, 3, 5, 6, and now you can map them to 1, 2, 3, 4. And the greater than lesser than conditions will remain the same. So this is basically similar to coordinate compression. So did you all understand how I found this recurrence? Actually, in the problem set, it was a bit slightly harder problem in which you needed to find the highest power of 2 dividing n. That is a number theory exercise which I have left to the reader. You can see. So it's basically an induction argument. So did you all understand the solution? How the recurrence is? Okay, so we can also like expand it. So n, we can also write it as so basically both of these notations are used for NCR and both are valid. Square and so on, we keep multiplying, and the second term will appear 2 times, the third term will appear 4 times, and we can write it as formally an minus k minus 2 an minus 1 k minus 1 minus 1 to the power 2 k minus 1, and we choose the appropriate values of k. We take k from 0, and the last term we want to do is basically 3, since a1 is equal to 1. Wait, basically here it's not meant to be a but 2. and we take it to the appropriate value of n minus 2. So did you all understand how I expanded it, the equation? If there are any typos, you can tell me. I basically expanded the recurrence again and again. So did you all understand this part? Okay, so now for more practice, I will show you how another example of solving a characteristic equation problem. Okay, so it turns out that in Google Jamboard, we cannot do more than 20 slides. I will just erase this. Um, Okay, I don't want to delete it. I will just erase it. Okay. So now the question is, I am giving you a recurrence. I will write it down. Xn equal to 3xn minus 1 minus 4xn minus 3. And now you are also given the initial terms. X0 equal to 5, x1 equal to 9, and x2 equal to 43. So now you have to solve the equation and find a closed form for it using the characteristic equation I told earlier. Now the characteristic equation for this will be x cube minus 3x square, and this will be a minus 4. Now why it's there's no x term because there's no n minus 2 term either. This will actually be a plus 4, and you have to like factor the equation to find the roots. So you can try a few numbers, and you can notice that. So if we try 1, it doesn't work. If we try 2, this will come out to be 8 minus 12 plus 4, which is 0. So x minus 2 works. We can divide the expression by x minus 2. And there are more roots also. So now you can easily factor it and find the roots in the quadratic. You get this equation equal to 0. Now the roots are obviously 2 comma 2 comma minus 1. These are the set of Ri's. And now you have to find the characteristic equation, not a characteristic equation, but a closed form from all of them. I will erase this. Now notice that this is a repeated root case. This is why I'm doing it. So to tell you how to handle repeated roots one. Now we can write xn as the roots are 2, 2 and -1. So c into 2 to the power n plus d into n into 2 to the power n. The n is here because it's a repeat term. If there are 3 repeats, we also add n square term. And e into -1 to the power n. So we write down the equation for the first 3 terms. X0 equal to c plus e, and x1 and so on we can write. I won't solve these equations right now, but there's a solution to these obviously. And the solution comes out. Wait, I should solve them. Okay, so this one is equal to 5. Now if we add 1, then 2c plus 2d minus e equal to 9, and x2 equal to 4c plus 8d plus e equal to 43, I believe. This is chat. Okay, so did everyone understand the characteristic equation part, how I generated the sequence? Please tell in the chat, or you can even speak. That will be. Okay, so solving for CDE. We will get an equation of the following form. I'm writing it out. C2. So this term will be 2 to the power 2n. This term, C8 term, this is not C. This term will come out to be 4 into 2 to the power n into n. And this term will be -1n. And the coefficient will be 3. Now all the relations are also satisfied. We can check. I'm checking. So yeah, all the relations are satisfied, and we get xn equal to 2 to the power 2n, 4 into n into 2n plus 3 minus 1 to the power n. So did you all understand this part, or how I found? This is important because of the n term. If there are multiple roots, you have to add terms with coefficients 1, n square, and so on till nk, if there are k plus 1 terms. So did you all understand how I found the closed form for this equation? You can even check for the first 4 or 5 terms and see it verifies. There are no square roots also in this term. So did you all understand? Okay, thanks everyone. That's all for today. And I may cover more advanced recurrences in the future. This is this was an introductory class, which emphasizes on finding basic recurrences, finding the characteristic equation. I also covered the closed forms and some interesting problems. Especially, I think that the Fibonacci number problem, where there's a Fibonacci number divisible by n, is very interesting. Thank you.
Yeah, thanks for the class. I'll stop recording.
Okay.